Uh, Good morning, everyone. I am Yogesh, a postdoc with Rama Govindarajan at the moment. And so I'll be talking on particle-laden turbulence with fast phase change. Um, it's to understand about cloud microphysics. Before I proceed, two things. First is acknowledgements to Dr. Bipin Kumar and Maumita, who are at IITM Pune, and they provide us with the DNS data sets that I will shortly talk about. And our predecessor, or like my predecessor, Jason, who was a postdoc here and currently at IIT Bombay as an assistant prof, and Manpreet Singh, who is a graduate student at the Yale now. And the second thing is, this talk is going to be more like descriptive rather than scientific. It's more like I have some hypothesis and then we did some experiments. We found some observations that are relating to this hypothesis. So do not expect much science from this. So without further ado, so what are clouds? So basic question, clouds are mixtures of air, water vapor, aerosols, ice particles, and liquid droplets. And then you find them in the sky, and I hope so it's not a clear day today. So how different is cloud turbulence from the conventional turbulence that you have actually looked at, like from yesterday's talks and stuff? So it's actually a highly turbulent, particle-laden turbulent flows with phase change. That is, you have water vapor condensing on nucleus or like these aerosol particles, and you'll find clouds being formed. So, and it's a huge problem, huge in the sense it has a wide range of length scales. Like in the spatial sense, it starts from like a few micrometers to an order of kilometers it goes. So it's like 9 orders of magnitude you have. And then in the temporal sense also, yes, like so this water vapor condenses on this nucleus within a few seconds or order of seconds, and then you have clouds spanning over months and stuff. And it's actually a difficult problem in the sense that you have to actually model the sub-Kolmogorov processes. That is, you have to track these particles as well as like monitor their growth and stuff. So a related problem that comes close to this is spray fuels, but they do not have this long range of length scales in that problem. So it's like most. And then where do we find these applications? It's just that to understand atmospheric dynamics, and then to forecasting weather, and then eventually like predicting the future climate, which will be the final goal. So why to study cloud microphysics? Because these microphysical processes are linked to the droplet evolution, which eventually become the clouds. So there are some key microphysical processes: droplet condensation and evaporation, preferential concentration of droplets, turbulent collision and coalescence, and then many others. So these three are the mostly looked after microphysical processes. So in this talk, I will be actually concentrating on these first two items, which are droplet condensation and evaporation, and preferential concentration of droplets. I will not be actually dealing with turbulent collision and coalescence, but we are keeping it for the future. So this cycle was actually shown by Ravichandran and Rama in that 2017 JFM paper. So this was actually done for a system of many vortices in a two-dimensional field with particles, or a field of particles. So what they said was that there is vorticity, and these vortices will actually eject these particles outside of them, and then you will find preferential concentration of these inertial particles. This preferential concentration will eventually lead to a inhomogeneous phase change. That is, where you have particles only, you will have these water vapor condensing on them. So like they act as cloud condensation nuclei outside of the vortices, and this inhomogeneous phase change will result in an inhomogeneous buoyancy, and because of this buoyancy, you will have a baroclinic torque, which is actually a source term in your vorticity equation if you rewrite your Navier-Stokes in its vorticity form. And then eventually you will have this cycle going on and on. So the question is, now this was actually shown in a two-dimensional turbulent box. Do we actually find it in a 3D cloud turbulence type of setting? So for that, like, we are going to look at the DNS data, a brief intro about the governing equations for the flow field, which is an incompressible Navier-Stokes with Busnik approximation. The Busnik approximation comes in this buoyancy term, where instead of the density here, we have written in terms of temperature. And then you have like scalar advection diffusion equations for the temperature as well as the mixing ratio for the water vapor, which is denoted by this QV, and it's defined as the density of the water vapor towards, or like the ratio of the water vapor by the density of air surrounding it. So when buoyancy is active, these two terms are like active scalars, and when it's not, it's passive scalars which are coupled to each other, that's it. So for the particles which are actually kept in a discrete sense, the governing equations are the simplified Maxi-Reilly equations, like you do not have the Bassett history term or the Coriolis force and so terms. Only the inertial term is considered in the acceleration term, and we also have the gravity into it. The additional thing that we are looking at here is the condensational growth of the droplets, and that is actually driven by the local supersaturation field given by this S. So the supersaturation is actually like just actually how much water vapor content is in excess of the surrounding air, that's it. And it has this condensational growth constant, which is actually a function of these quantities, but it's not a very important thing. Okay, so the simulations are actually done in a half-meter cube box of length half-meter cube with 512 cube grid points, and then approximately 7 million particles, which gives a number density of 50 per centimeter cube, which is on the range of what you find in clouds. In clouds, you find actually something like 10 to 100 per centimeter cube, but we are like something like an arithmetic mean of it. And we consider like two droplets, but two sizes of droplets. One is 30 microns and 10 microns, but here I will be talking mostly about the 30 micron, which are like more inertial compared to the 10 micron droplets. And we have like 4 cases, which is buoyancy plus gravity. That is, we have the buoyancy term active in the flow equation, and then the gravity term active in the particle equations. And so in that case, we do not find droplets clustering around, and then when we have no buoyancy and no gravity, we find droplet clustering. And in case of buoyancy with no gravity, or like without gravity, we have droplets clustering around. But without buoyancy and gravity, we do not find droplets clustering around in this thing. So these are the 4 cases. So just remember this notation type thing. Okay, so first part of the cycle, that is vorticity leading to preferential concentration of inertial particles. The usual indicator that many use is the Q criterion, which says like if it is greater than 0, you have vorticity, or like the regions that you identify are vorticity dominated, and if it is less than 0, they are actually strain dominated. So what is being shown here is actually the 4 cases for like at an instant of time. And then on the y-axis, you have the probability. The probability is actually like the number of grid points having this value in x divided by the total number of grid points. It's not the PDF. You just actually have to scale it with the width of each of these bins to get the PDF, but it just makes the point here. So what does this mean? So the red one corresponds to the flow field. The blue one is for the droplets. The flow field is, if it's like 10 power minus 2, it's a 512 cube box. So you have like 140 million points. And so it's like 10 power minus 2 of it. So between Q equal to minus 100 to plus 100, you have like 1.4 million grid points having that value. Whereas for the particles, it's only 7 million. So it's like approximately 70,000 having that power number. So what is interesting in this is that like in presence of gravity, you do not actually find any alignment of these curves. Whereas in the absence of gravity, we find that the particles are slightly aligned towards the strain-dominated regions. So droplets do not show preferential alignment when there is droplet settling in this. So now to the next part of the cycle, which is like if there is preferential concentration, do we find inhomogeneous phase change? So again, we actually use the Q criterion now that we condition the temperature profiles based on the Q criterion values that we have. So what is shown again is the probability, the same concept, the number divided by the total number. And what is shown here is the flow temperature on the x-axis. and then Q less than 0, which is the strain region, that is the red curve, and then the Q greater than 0 is the vortex dominated region. So what we find here is that there is a slight shift in the mean value. Though it is small, it could be significant locally. It's a work in progress, and then we are actually looking at various parameters so that like we can identify a real cloud-like setting where this difference would be like much larger. But still, like this difference is quite significant. And we find it only in the cases of without any gravity in the particle equation. So I'm not going to show you the other curves which are like going to be like on top of each other. So now I'm going to just skip this inhomogeneous phase change to buoyancy thing. There I have to actually like show about the supersaturation fields, but sort of brevity, we just, like I'm just going to skip this thing, but you just take it on face value that this process also exists. So now for this, to understand this, I'm going to show you about the energy spectrum. So what is shown here is the compensated energy spectrum, total kinetic energy of the turbulent kinetic energy, for the case without buoyancy and with buoyancy. So with buoyancy, like as the time increases, we find actually a different dynamics happening in the larger wave numbers, that is like the smaller length scales, so which is usually related to the vorticity. So I know that I'm actually kind of hand waving here, saying that, oh, look at like turbulent kinetic energy, and then I'm talking about like vorticity being produced. But vorticity do actually be found in the small scales, and maybe later I would be actually giving you a proper indicator for this. So that's about it. In the summary, what we understood is like preferential concentration is essential for phase change, and that is actually only observed in very large droplets, that is droplets with large inertia. And then though this temperature change is actually very small in the average, maximum temperature changes in a cloud are much less than a degree. So this actually is a starting point for us to actually look further into this. So these are some of the ongoing works that probably in the next talk, I'll be giving a good idea about this. Thanks. Any questions?
Questions? Okay. Okay, if we have no questions, then we thank the speaker again. And